Hi everyone. Earlier this year I discussed the game of Tic Stac Toe. It's a 3D tic-tac-toe game, and I finally got a set, so I thought I'd show a game against Deep Nikita. I've since updated my program to do machine learning, which I kind of discussed of how it would work out in my last video. So we're going to play a game against Deep Nikita. I'm going to give it 5 seconds per move, just so that this can fit comfortably in a video. And we're going to go first. So it also thinks during our turn, so it's pondering right now because it's our turn. Just from experience, I know the corner is a good move, so we're going to start there. And that corresponds to A on my program. Computer is thinking, and it has gone diagonally to us. That corresponds to over here. Usually another corner is a good idea, so we're gonna go M, and it's probably gonna take the last corner of D. There it is. There are a few things we could do. We could make a thread that it has to respond to, so we can build on top of that. That's usually what I do. Not that I'm any good at this game. By the way, let's stop and look at some of the numbers. Negative numbers correspond to O being ahead. Positive corresponds to X being ahead. Unfortunately, we are behind a little bit. And, just one improvement I could make is that the computer could have made that move automatically. I just haven't gotten around to making a few. That's only a 2-line change, really, with what I have. So the reason I like that move is it allows me to build on top. So we can make the move E. It's thinking either H or I, and it did H, and that corresponds to this one. I find if I put it out on the board, it's a lot easier to visualize the threats. Sometimes threats like these I could miss on the screen just because of how spread out they are. So obviously we're going to go to L. By the way, I haven't gotten to the blocker pieces. Those black pieces over there, I'll discuss that in another video coming up. It's a little bit more involved. The traditional version, Tic Stac Toe actually has a longer history than this version itself. It used to be called Score 4. And Score 4 was played without those black pieces, so I'll get to them in a future video. It's a little bit beyond the scope of this video, just because I haven't really programmed it. So this would make a number of threats, so we should try that out. And that corresponds to I. And the computer goes here. That makes sense. Maybe here, because now we're building a diagonal line. And that course. Okay, so let me talk a little bit about the machine learning algorithm at hand. What is done is that on the board, there are 64 cells on the board. There are 76 lines that can win. Basically, you have horizontal, vertical, up and down lines. You got the diagonals, you got space diagonals, It turns out there are 76 of them, and there are 18 non-isomorphic classes of lines. So for example, this line is really isomorphic to this line, and then this diagonal is isomorphic to this diagonal. It turns out there's 18 different classes of them, and for each line you got well, there are a few ways to look at it. You've got 3 to the 4 different ways the line could be occupied, right? Because each cell could be an X, an O, or it could be empty. But there's more to it, because if it's empty, it could either be an immediate legal move, it could be 1 away from being a legal move, it could be 2 away, or it could be 3 away. So each cell really has 6 different states that it could be in. And so each line has basically 6 to the 4 different states that it could be in. I apologize, where'd the computer go? Here. So each line could have 6 to the 4, and we said there were 18 non-isomorphic lines. So we got 18 times 6 to the 4 different weights to learn. So for example, a line that looks like this gets a certain value associated with it. A line that looks like completely empty at this level gets a certain weight associated with it. The reason I love this evaluation function, and I'm still doing testing to see how it looks like, the reason I think it will do very well is that a lot of decent evaluation functions for Tic Stac Toe and Tic Tac Toe related games rely heavily on, I apologize, what did the computer, oh, I put the piece in the wrong place, that's why I'm confused. But the reason that I like having a weight associated with each line state is a lot of good evaluation functions for Tic Stac Toe rely heavily on how many lines are free. So for example, one common function is to count how many of the 76 lines are free of your opponent's pieces, and you do that for both sides. And the side that has more free lines is ahead. Having a weight associated with each line is clearly at least as good as that, because it's going to capture that idea, except it might give a different weight for each line being free. And that function already does pretty well. It doesn't capture parity, of course, but that function captures a lot of different things. And machine learning to capture weights could potentially capture parity issues. So it's basically the function of how many free lines we have kind of on steroids. It's at least as good as that, potentially more, and the amount of memory it takes is pretty decent. It's not a whole lot. I can show you the file later on. And then there's some tweaks to that based on different stages of the game. Obviously certain lines are worth more in the opening than the end game, so there are some tweaks to it to have different values of weights depending on the stage of the game. Where did the computer go? X. There it is. I think this is the longest I've ever lasted in a game against my program. Usually I lose very early on. I think it probably helps because I have the board out. Usually I just miss a line altogether. The computer thinks it's very close to winning, the way I set up my evaluation function is that it learns a win as a negative, it learns a white winning as a -1. So it's getting there. It thinks that this is a potentially theoretical win at least. Okay, so it looks like we gotta block this line now. And that corresponds to F. You know, it'd be really nice if I got in touch with somebody who knows a little bit about robotics and have the computer actually make the moves of, have some kind of robot arms that interface with Deep Nikita to have the computer make the moves. That would be really cool. But here. I'm just really glad to have lasted this long. Usually I lose very early. Let's see, this would block a line and also help us set up a diagonal. And B here. Oh, it found a theoretical win in 9 moves. 7 moves now. What did it do? It went to L. So I see what it's doing. It's creating a diagonal line here. Let's see. We can probably stall it by creating a threat here. Now it has a win in 5. Up here. I'm really excited because if this does really well, I'm thinking about using the same strategy for Connect 6, which is a very interesting game. Connect 6 is very far from being solved. This game could potentially be solved someday. It's kind of interesting because there's a related game called Cubic, which is basically 4x4x4 Connect 4, except it doesn't have the gravity rule. And that is solved. And for some reason, the gravity rule makes it more tricky. I'm not sure if that cubic game is weakly solved or strongly solved. It's probably only weakly solved. That's why the gravity rule makes it a little bit tricky. Let's see. Oh, it's threatening a win here. Oh, I see. Now it has 2 stack threats. Okay, so K. And yeah, I really need to have my program make these force moves automatically. It's you don't want to waste too much time. There's time limits at different computer gaming contests. And there it is. O wins. It's kind of hard to see. There it is. Alright, thanks for watching. Oh, by the way, it seems like it thinks that one of these pieces is a face. The camera just highlighted a face somewhere. Thanks for watching.